Hello, fellow learners. Welcome back. It is time in that point of the year for stoichiometry. Kind of sounds like a scary word, but it's really not that bad. So, here we go. Teach me how to stoic. Teach me how to stoic. So all stoichiometry is using balanced reactions and the ratios that you find in there to get from one species in a reaction to the other. So you can kind of look at a reaction kind of like a recipe. A recipe does the exact same thing. It tells you how many of what ingredient to put with how many of another ingredient to get the product that you want to make. Sometimes that means 2 sticks of butter for every 1 bag of chocolate chips to make chocolate chip cookies. But in chemistry, it might mean 2 moles of hydrogen gas to every 1 mole of oxygen gas to get water. It's all just calculation of quantities. So if you think of this in something real concrete, like a bike reaction, you put together a bunch of different ingredients or parts. So to put together a bike, we need 1 frame, we would need 1 seat on most bikes, we would need 2 wheels on most bikes, and 1 handlebar set, plus 2 pedals. So these are all just ratios of how many of each part goes into that 1 bike. There's 2 pedals for every 1 bike. There's one handlebar for every 1 bike. So we're going to be using these ratios in chemical reactions now. So if we think of a chemical reaction example, like nitrogen gas plus hydrogen gas gives us ammonia, we have some ratios that we can put in here. So our first step, what we should always do when we see a chemical reaction, is to balance it. Balance it. So we have 2 nitrogens here, we need 2 nitrogens here. We now have 6 hydrogens here, so we need a 3 right here in order to balance it. It's balanced, woo, it's a happy reaction. So if we look at what that reaction tells us, we know that for every 1 N2 molecule, because we can say that there's a 1 in front of here, we can make how many NH3 molecules? Well, for every 1 of these, we have 2 NH3 molecules. For every 3 H2 molecules that we put into this reaction, we can make 2 NH3 molecules. And for every 1 NH2 molecule, we need 3 H2 molecules to go with it. So we're using these coefficients out in front just as ratios and how many go with each one. It's all just a bunch of ratios. So if we think about this in another way, we could also say that for every 1 mole of N2, we can make 2 moles of NH3. For every 3 moles of H2, we can make 2 moles of NH3. Those coefficients can mean molecules. Those coefficients could mean moles. It just depends on the quantities that we're working with. So either way, though, they all mean the same ratio. 3 to 2, 1 to 2, 1 to 3. They're all going to be ratios with each other. This comes down to the law of conservation of mass, which we learned about in reactions, because we can neither create nor destroy matter. When we do reactions, there isn't a higher being that just throws stuff in or takes stuff out. Everything on the reactant side has to equal everything on the product side. And when we balance things, this is called the law of multiple proportions. So different compounds are formed by the combination of the same elements. These elements will always combine with others in a ratio of whole numbers. You're never going to get half of a hydrogen here. It's always going to be NH3. We can't split atoms when we're doing reactions. We're working with the electrons in reactions, and they're just recombining in different ways. So now stoichiometry is just going to use those ratios to get from one thing to the other. We've been using one side of our mole map because we've been working with one compound. If we have moles of something, we can get to volume of the same thing. If we have moles of something, we can get to grams of the same thing. This is all just one compound. But in a reaction, we have different things, and we want to know how to get from one thing to another. So, yeah, it's time for your roadmap to mole success. So when we are looking at our mole map now, we have this side. This is what you have. But we're going to add kind of a mirroring side now. In order for one substance, if you're working with one substance to get to the other, we can use a mole-to-mole ratio from that balanced equation to get from moles of something to moles of something else. Therefore, we also know how to get from moles of something to volume, to atoms or molecules, or to grams. So as long as we have this mole-to-mole ratio, we can get from one substance in the reaction to another, just from using the balanced equation. So that means all of these are still going to stay the same. As long as we're working with one substance in grams, 1 mole is always going to be equal to the molar mass. To get us to moles, one mole is always equal to 22.4 liters of gas at STP of that same substance. The only thing that's going to be different here is the mole-to-mole ratio. So we have 1 mole, 1 mole, 1 mole, 1 mole, 1 mole, 1 mole. The only place that it won't be 1 mole is possibly right here. It could be 1 mole, but not always. So keep that in mind. The only place that it may not be 1 mole is in this middle. So don't be writing anything except 1 mole on all these others. So let's try this out with an example. If we have 45 grams of ethylene, how many grams of carbon dioxide will be produced? So we have 45 grams of this one, and we are looking for the number of grams of CO2. Now, what's the first step whenever you see that reaction? You should say to yourself, I got to balance it. So when we balance this, we have 2 carbons, 1 carbon, so we need a 2. We have 4 hydrogens, 2 hydrogens, so we need a 2. We now have 2 oxygens here, 4 here, so 6 on this side, so we need a 3. So now that our reaction is balanced, now we can use some stoichiometry to get from one substance in this reaction to the other. So if we start with 45 grams of C2H4, we know that according to our mole maps, grams to moles, the only way to get from one to the other is mole to mole. So we need to get to moles from here. So we know that we can put moles on top because that's where we're going, grams on bottom, and to go from grams to moles is the molar mass. If we add up 2 carbons and 4 hydrogens, our molar mass of C2H4 is 28 grams, not 24 grams, 28 grams. Okay, so our grams of C2H4 cancel out. Now at this point in the class, it is very important to watch your labels, because if you just start putting grams and moles and moles and grams, you won't always be sure which grams or which moles you're talking about, because we're working with multiple substances now. So make sure that you put all of your labels into your work. So right now we're in moles of C2H4. We have to get from C2H4 to CO2. The only way to do that is our mole-to-mole ratio, and that comes from our balanced equation. We know that for every 1 mole of C2H4, we have 2 moles of CO2 from our coefficients out front. So moles of C2H4 have to go on bottom because that is what we want to cancel out. Moles of CO2 have to go on top, and we have 2 moles of CO2 for every 1 mole of C2H4. Moles of C2H4 cancel out. So now we're on the other side of our mole map in moles of CO2 into our second substance, and we have to get that to grams. We're trying to find the number of grams of carbon dioxide. So our moles of CO2 go on bottom, and on top are our grams of CO2. In order to get from moles to grams of something, we use the molar mass. So 1 mole of CO2 using the molar mass, carbon is 12, oxygen is 16, 2 oxygens, 44 grams. Moles of CO2 cancel out. We are left in grams of CO2, which is what we need. So just like what we've been doing, multiply across the top, divide across the bottom, and you should get an answer around 141.4 grams of CO2. So pretty much the same stuff that we've been doing. We just added the one step going from mole to mole so that we could go to different substances. Let's try another. How many grams of nitrogen dioxide, so we are looking for how many grams of this, are required if this reaction to produce 5 liters of HNO3 gas at STP. So we have 5 liters of this one. And you should say to yourself, so first thing I should do when I see that reaction, balance it. So if we have 1 hydrogen here, 2 here, we need a 2 over here. We have 2 nitrogens here and 1 nitrogen here, so 3 on this side, so we need a 3 over here. We have 6 oxygens, plus 1 is 7. We have 6 oxygens here, plus 1 is 7, so it's balanced. All right, so now we can start with our stoichiometry. Again, start with what we know, and we know that we have 5 liters of HNO3. So that means that we are starting at the volume part on the map. We are trying to get to grams of something else. So if we look at that pathway, we're going to have to go volume to moles, moles to moles, moles to grams. So volume to moles, liters on bottom, moles on top, because that's where we're going. And we know that 1 mole of HNO3 is equal to 22.4 liters of HNO3 at STP. So our liters are going to cancel. We're in moles now. And now to get from moles to moles, we use the balanced equation. So our moles of HNO3 is going to go on bottom. Moles of what we're going to, which is our NO2, is going to go on top. And from our balanced equation, we know that there are 2 moles of HNO3, and there is 3 moles of NO2. Moles of HNO3, gone. They gone. All right, last step. We have to get from moles to grams. So moles are going to go on bottom, so we can cancel them out. And we're going to grams of NO2. And we know that to get from moles to grams, we use the molar mass. So 1 mole is equal to, nitrogen is 14, oxygen is 16, so our molar mass, 46 grams. Moles of NO2, they gone. We are left in grams of NO2, which is what we wanted to find. Again, multiply across the top, divide across the bottom, and you should get something around 15.4 grams of NO2. Hopefully this isn't too confusing for you. We're just adding kind of one more step onto our mole maps here. And if you have any questions, feel free to come in and ask me about it. Otherwise, we will be practicing this in class the next time I see you. Have a good day, evening, whenever you're watching this video. Peace out.